Good afternoon, ladies and gentlemen. Welcome to another exciting episode of Dave Does Math from Home. In the last episode, we talked about how to find the derivative at a point, and the output of that entire process was a number. That number was a slope. That told us at that point, the tangent line to whatever function we were using had a slope of that number. Today we're going to spice things up. We're going to make it much more interesting. I'm no longer interested in derivatives at points and the output being numbers. Now I want derivative functions. So a lot of this process is going to be the same. We're still going to be using difference quotients. We'll still take limits. The big difference is we're not going to use an a value. In the last lesson, the process that we engaged in was we had a function and a number, and we put both of those things into the difference quotient at the same time. We did all these calculations, and then we took the limit, and we got a number. This time we're going to do all of that, except we're not going to use the a value right away. We're going to do the difference quotient with the variable x and the variable h, both in there as variables. So we're going to do this computational process with two variables, x and h, in it, and they both stay. At the end of this process, we'll take the limit where we set h equal to 0, and the output of this will be a formula or an equation that probably should involve some x's. That's the derivative function. It's not going to be a number anymore. It's not just a slope. Now it's going to be a function which we can use to find the slope at any x value. So you can plug in any x value you want after we have the derivative to get the slope at that point very easily. The other very interesting thing this process is going to open up is if we can get derivative functions, it means we can graph derivatives. So stay tuned for that. We're going to start with some calculations and see what those look like. In the last one we started with polynomials. Let's start with polynomials again. Polynomials are pretty straightforward. Let's do f of x equals, we'll do an x squared, no, we'll do 2x squared minus 7x plus 29. This is a pretty exciting looking quadratic. It's kind of a mess. Not something I'm interested in factoring or doing anything with, but we can take a derivative pretty easily. I'm not going to give us an a value. We're just going to do it right from here. The other fun thing I need to introduce is some notation for derivatives. For now, we are going to call the derivative function f prime of x. Prime is like you put a little apostrophe on top of the f as if it was a subscript. This isn't the number 1, it's just a little like dash. It's like an apostrophe. So this is read f prime of x. It means the derivative function, and the derivative function is the limit as x approaches 0 of f of x. Sorry, not x approaches 0. Ooh, that was bad. Sorry. The limit as h approaches 0, f of x plus h minus f of x all over h. This is the derivative. And again, every time you do one of these problems, you should start by writing down this derivative. This is an excellent step 0. Just write this exact thing, word, symbol for symbol every time, and then start to go from here. In step 1, I'll plug in this function into the difference quotient. So f of x plus h should give me 2x plus h squared minus 7x plus h plus 29. This is my f of x plus h. From this I need to subtract f of x, which is 2x squared minus 7x plus 29. And all of this is divided by h. Now we need to do some distribution. I said back in section 1 that when we do these problems, the number one mistake people make with these is distributing things. We have to distribute things on multiple levels here. We need to distribute the x plus h and the x plus h in this squared business. That's going to be a FOIL process. We need to distribute the -7 in here and then the 2 into the result of this FOIL business. We have to do the exponent first and then the 2. We have to distribute this negative sign to all of these things. There's a lot of distribution going on in here. It's easy to forget something and make a mistake. We have some checks after this step to make sure we've done it right. But for now, just try to remember to distribute everything. I'm going to do it all at once. I know that x plus h squared is going to be x squared plus 2xh plus h squared. And then when I distribute the 2 in there, I should get 2x squareds, 4xh's, and 2h squareds. Distributing the 7 should give me -7x minus 7h. The 29 can just hang out. And then I distribute this negative sign. I get -2x squared, positive 7x, and -29. And all of this is still divided by h. So now we can start to look for some of these checks to make sure we did everything right. And there's two sort of key things you need to look for. If you did this distributing step correctly, two things should happen. The first thing that should happen is everything that does not have an h in it should disappear. This doesn't have an h in it. Does it disappear? It does. This has an h, it can stay. Has an h, it can stay. No h's. It should disappear, and it does. This has an h, this has no h's, and it disappears. So, everything that has an h is allowed to stay. Everything that does not have an h should cancel. And the things it should cancel with are all just the back end. This minus f of x piece, this is the piece that doesn't have any h's in it. This entire thing should cancel. Like each piece of this individually should just cancel with a piece of the original. So all of these things cancel, and now we have the limit as h goes to 0 of 4xh plus 2h squared minus 7h all over h. Because the only things left on top have h's in them, we can cancel that with the h on the bottom. That'll give us the limit as h goes to 0 of 4x plus 2h minus 7. And now at last we can execute plan B by setting h equal to 0 because it's no longer part of the denominator. And we will get 4x minus 7. And this is f prime of x. F prime of x is 4x minus 7. The derivative of this quadratic, of this parabola, is a linear function. So, if I wanted to know, so in section 3.1, we were doing this with specific points involved. We were finding the slopes of these derivatives when like a was 2 or a was 5 or whatever. We can still do this here. We just make the original process a little bit more difficult, or a little bit more, just more messy. I don't know, maybe it's not more difficult. We make the original process a little bit more messy by keeping these things as x's instead of using numbers for them. But the result is a nice clean little formula down here, and now we can plug whatever we want in for x. So, if I find out later that I want the slope when a is 2, I can just find f prime of 2. It should be 8 minus 7, that's 1. Okay. If I want the slope when a is 5, then I can just do f prime of 5. That's going to be 13. Easy. Effortless. Getting here is more work, but once you're here, finding slopes at specific points is very easy. The other cool thing we could do about this is we could find, if we were interested in where the slope had specific values, we could do that. Like if I wanted to know where f prime of x equals 0, if this was my question, I could just set this equal to 0. 0 equals 4x minus 7. X is probably going to be 7/4. There. This is the point where the slope equals 0. This idea in particular is going to be very important later on when we talk about maximizing and minimizing functions. That's one of the most important things we do with calculus, is find where these functions have maximums and minimums. Functions have maximums when the tangent line is 0, or minimums when the tangent line is 0. So every time you get a tangent line that's flat and horizontal, you know that's either because it has a minimum there, a minimum there. Let me make sure my gestures match my words. Either it has a minimum there, and the tangent is 0 and flat, or it has a maximum there, and the tangent is 0 and flat. In either case, that's important information. And this function has its minimum or maximum value here when x is 7/4. So that's basically the big change we're doing in this section. It's almost exactly what we did in the last section, just in a slightly different order. Instead of putting in an a value in here, we'll put the a value in at the very end, after we leave this thing as an x the whole time, and get a derivative function. And then we can plug our a values into that derivative function. It's nice and straightforward. I'm going to talk a little bit about what these derivative functions look like graphically. So let's say we have a function that does this. This is y equals x squared. Without doing any analytical math on this y equals x squared graph, I want to see what the derivative is going to look like. Back here, the derivative should be very negative. The slope on this back end is extremely steep and negative, so I'll get a value that's down here. As we move forward, so this is the super negative value. Let me actually do this in a different color. If I can get a different color. We'll use red. Red seems good. Back here, the slope of this is very negative, so I'll get values that are down here. Over here it's kind of negative, still going down, pretty steep. Over here it's still negative but pretty tame. Right here the slope is 0. Here the slope will be very slightly positive. Here it'll be more positive. And over here it'll be extremely positive. The slope gives me a straight line like this. I don't know if that's showing up on the camera, these markers. Not long for this world. Hopefully that's a little more clear. The slope of this is a straight line. It goes through 0, 0, because that's where the original function has its maximum or minimum. This point, the vertex of the parabola is where the tangent line is flat. If the tangent line is flat, the derivative is a value of 0. If we do this analytically, the derivative is the limit as h approaches 0, f of x plus h minus f of x all over h, which means that it is the limit as h approaches 0 of x plus h squared minus x squared. That's the limit x squared plus 2xh plus h squared minus x squared over h. X squareds cancel, and the h will cancel from here. We get the limit as h approaches 0 of 2x plus h Now I can plan B this to get 2x. This is f prime x, which matches exactly what we just found on this graph. The graph here should be a straight line through 0, and it is. It is a straight line through 0. Goes up. So, you can sketch graphs of functions. You don't have to do the analytical stuff. You can just look at the graph of a function and kind of sketch what you think the derivative approximately should look like by looking at its slope in various places. Big negative slopes means the derivative has negative numbers. Big positive slopes means the derivative has positive numbers. Flat slopes means the derivative is 0. That's pretty much all we're going to do in this section. We're going to do difference quotient derivatives using x values instead of a's, or using x variables instead of a values. And we will look at graphs of things and construct graphs of derivatives. Should be pretty straightforward from that. Let me know if you have any questions. Stay tuned for the next one.